Welcome to this lecture. This is the second lecture of week 4. In this week, we are concerned with properties of various modes of convergence of random variables that we have already introduced. Namely, there are three types of convergences that we are considering: convergence in LP, almost sure convergence, and convergence in probability. Recall that we have already compared between these three types of convergences, and in the first lecture of this week we have looked at two important properties, namely the metrizability, and also we have discussed results involving the uniqueness of limit in each cases. In this lecture we will continue talking about various other properties, but specifically those related to algebraic structures of this type of convergences. Without further delay, let us continue the discussion with lecture notes. Alright, so as pointed out, we are now concerned with algebraic properties of the three types of convergences: convergence in LP, almost sure convergence, and convergence in probability. As always, we will continue to assume that all the random variables that we are looking at are defined on a single probability space defined as this omega f p. Now, this is the first result of today's discussion. We are looking at continuous function on the real line taking real values, and if we are given these random variables x, x1, x2 and so on defined on this probability space, then in that setting we have these implications that if x n converges to x almost surely, then f of x n, this is again another sequence of random variables defined on the same probability space, converges to f x in the limit, but the mode of convergence remains with almost sure mode. And a similar statement can be made for convergence in probability, meaning if the sequence of random variables x n's converge to x in probability, then the new sequence, which is f of x n, converges to f of x again in the convergence in probability sense. So, this is called the continuous mapping theorem, and this holds for almost sure convergence as well as convergence in probability. And all we require is that this function f that we are considering is continuous. Here one technical point that we have to take care of is that f is actually measurable with respect to the Borel sigma field on the real line. So, if you are looking at a continuous function on the real line, then it is measurable with this structure, and therefore, if you are looking at f of x for example, that is definitely a measurable function from this probability space to the real line with the Borel sigma field. So, the measurability structure is kept intact as long as you assume f to be continuous, because continuity implies the Borel measurability in this situation. So, let us move on and see the proof of these results. We start with the assumption that the sequence that we are considering is converging in the almost sure mode of convergence. Now, as per definition, there should exist a set coming from the sigma field with probability 0, such that on the complement of the null set we should have the pointwise convergence, meaning if you choose any such omega from the complement, then x n of omega, this sequence of real numbers as n goes to infinity, converges to x of omega. Now, this is just by the definition, but now we appeal to the continuity of the function that we are considering, and then here is the sequential criteria of continuity that we are all aware of, and therefore, we will immediately have as a standard consequence of continuity that the new sequence which is given by f of x n evaluated at this point omega, those numbers as n goes to infinity converges to f of x of omega. This is just by the continuity of the function, and hence what we ended up having is that the set A still has probability 0, and on the complement of the set A I have the required convergence, and hence we conclude that f of x n converges to f of x in the almost sure mode of convergence. So, this statement is quite easy to prove. Let us see how do you prove the similar statement, but when we are considering the convergence in probability. Recall now that in our previous lecture we had discussed in note 2 that for convergence in probability, every subsequence of the original sequence will be having a further subsequence, let us denote it by x n k l, such that the further subsequence converges to the limit random variable, but in the almost sure mode of convergence. But now this is in fact a equivalent criteria for convergence in probability, that convergence in probability holds if every subsequence has a further subsequence converging to the limit random variable in the almost sure mode of convergence. We are going to use this important identification of convergence in probability in our proof. So, let us see how do we use this result. We start by looking at this almost sure convergence for the further subsequence that we are considering. Again, since the function f on R to R is continuous, we just use argument similar to the previous part. By part 1, we will immediately have the almost sure convergence for this specific sequence of random variables as L goes to infinity, and this mode of convergence is almost sure mode of convergence. But now let us look at this sequence f x n k of the original sequence f x n. Now this original sequence, if you consider this specific subsequence which is now denoted by f x n k, then that has a further subsequence which is now f x n k l. So, as L goes to infinity, we have star which is in the almost sure mode of convergence. Therefore, considering the original sequence as f of x n, this has further subsequence and the further subsequence of that converges in almost sure mode of convergence. Therefore, by the sufficient condition part of note 2, we conclude that the original sequence must converge in probability to the limit random variable f of x. So, we have crucially used the characterization of convergence in probability, that every subsequence will have a further subsequence that converges in the almost sure mode of convergence. And we have used the part 1, that was the continuous mapping theorems involving the almost sure convergence for our argument. So, therefore, using part 1 and this identification of convergence in probability, we have ensured that the continuous mapping theorem continues to hold for convergence in probability. Now, here let us go back to the statement that we had looked at for the continuous mapping theorem. Now, let us try to understand what type of examples we can have. Now, let us see that if we look at the function, let us say f x equals to x squared defined on the real line. So, this is a nice continuous function, and therefore, as a consequence we will be having the fact that any convergent sequence, be it in the almost sure mode or in the convergence in probability mode, in either case the corresponding squares which we will obtain as a action of the function that we are considering, the square function, we will have the x n squared will converge to x square. This is not only restricted to the square function, we can choose any of our favorite continuous functions. For example, taking the trigonometric function, let us say sin of x. So, this is small x mapping to sin of x, we can again conclude that sin of x n will converge in the almost sure mode or in the convergence in probability mode to sin of x. So, by looking at many other continuous functions, we can conclude the convergences for these type of new sequences of random variables. So, this is the application of continuous mapping theorem that will help us appeal to the continuity of the function and give us the relevant continuities. However, this is an important comment that we have proved the continuous mapping theorem for the almost sure mode of convergence and convergence in probability. The other mode of convergence that we know about, which is convergence in LP, that actually does not support continuous mapping theorem. In fact, you can find a sequence of random variables converging to x in L1, but the corresponding sequence after applying the function does not converge in L1. So, this is left for you as an exercise. Please figure out such a sequence which converges in L1, but after applying an appropriate continuous function it does not converge in the L1 mode of convergence. So, this will tell you that the continuous mapping theorem does not hold for convergence in LP, and we are showing that for the case p equal to 1. And similarly, you can try to construct examples for other values of p. So, we move on and look at further algebraic properties of these various modes of convergence. To start off with, we will concentrate our attention to the mode of convergence in LP. So, here what we assume is that we will have these random variables all defined on the same probability space. So, this part is giving you a sequence x n, and we will be concerned with its limit random variable, which will be typically denoted by x, and there is another sequence of random variables which is y n, and for which the corresponding limit random variable will be denoted by y. Now, we are assuming that all these random variables are defined on this single probability space, and here we have several statements. So, the first one involves scalar multiplication, and for that we choose a scalar alpha coming from the real line. Then for any number p between 1 and infinity, both 1 and infinity included, if we are given the LP convergence of the sequence to the random variable x, then we conclude that alpha times x n also converges in LP to alpha times x. So, this is the first statement which we claim. The second statement is concerned with addition and subtraction. What do we have is this: we are assuming that a number p is again between 1 and infinity, both 1 and infinity included. Then if both these sequences are converging in LP, meaning x n converges to x in LP and y n converges to y in LP, then we conclude that x n plus y n converges to x plus y and x n minus y n converges to x minus y in the LP mode of convergence. So, here the notation means that each of these convergences are either for the addition or for the subtraction, meaning x n plus y n converges in LP to x plus y, and similarly we read the result for the subtraction. Alright. So, let us move on and see other algebraic operations. The next operation that we will be discussing is the multiplication operation. Here there are these assumptions that we will use, that we are choosing numbers p and q between 1 and infinity. Both 1 and infinity are excluded in this case, and moreover what we will assume is that p and q are related in this way, that 1 by p plus 1 by q is equals to 1. So, recall that this is the setting of the Holder's inequality that we have discussed earlier, and as we shall see in the proof, the Holder's inequality will play an important role. Now, we are considering these modes of convergence, that for the first sequence which is x n, it will converge to the limit random variable in the LP mode of convergence, and the second sequence y n converges to y in the LQ mode of convergence. Then the claim is that x n times y n converges to x times y in the L1 mode of convergence. So, this is the claim. And finally, what we are interested in are certain changes in the assumptions. So, here we are concerned with different modes of convergence or different regularities of convergence. The first one was in the LP mode of convergence and the second one was LQ, and we claim that the product is converging in L1. Now, what we are going to see is that one of them we will consider in the L1 mode of convergence and the other in L infinity mode of convergence, and we will conclude the same thing, that x times y, that will be the limit random variable in the L1 mode of convergence for the sequence x n times y n. So, here the first sequence is converging in L1, the second sequence is converging in L infinity. So, this is the conclusion that we are drawing. So, let us see the proofs of these results one by one. We first start with the scalar multiplication result. So, we are assuming that the sequence converges to x in LP, and here the definition tells you that the p norm of x n minus x goes to 0 as n goes to infinity. Now, let us bring in the scalar multiplication. So, for alpha in the real line, note that alpha x n minus alpha x, the p norm of that can be computed as mod alpha times the norm of x n minus x, and that is what we use, and if you take limits in that relation, then we end up with the fact that it is mod alpha times the limit of norm of x n minus x. But as per our assumption, this limit is 0 and hence the limit of the p norms of alpha times x n minus alpha x, that also is also 0, and hence we conclude that alpha x n converges to alpha x in the p norm, and therefore, it is in LP mode of convergence. So, this result is very easy to prove by looking at the properties of the norm function. Similarly, we are going to see that estimates involving the norm function is going to help us proving other of these statements that are included in the main theorem. So, the next one is concerned with addition and subtraction. So, let us see. So, here what we appeal to is the triangle inequality for the norm. So, this we have discussed earlier and called it the Minkowski's inequality. Let us see. So, what we are now looking at is either x n plus y n minus x plus y, or we are going to look at x n minus y n subtracted with x minus y. We are going to be concerned with the p norm of that. So, if we appeal to the triangle inequality for the norm, then it is dominated by p norm of x n minus x and addition with p norm of y n minus y. But now, if x n converges to x in LP and y n also converges to y again in the LP mode of convergence, then both these limits are going to 0 as n goes to infinity, and hence by this above triangle inequality we will claim that x n plus y n minus x plus y, the p norm of that is going to 0 as n goes to infinity, and x n minus y n minus x minus y, that will also go to 0 in the p norm, and hence we get the convergence in the LP mode of convergence for the addition operation as well as the subtraction operation. So, this is giving us very nice algebraic operations for the convergence in LP. Let us now look at the multiplication operation. So, here as mentioned above, we are going to appeal to the Holder's inequality for the norms. The first thing that we concern with is that the product random variable is in the correct space. So, here we are considering the situation that x is in LP and y is in LQ, and since p and q are satisfying this conjugacy relation, then by the Holder's inequality the product must be in L1. So, that is the first application of Holder's inequality in this argument. But moreover, we have discussed earlier in corollary 5 of week 1 that the norm function is actually a continuous function on LP spaces, and therefore, as long as x n's converge to x in the p norm, then the p norm of x n must converge to the p norm of x. So, this was discussed earlier in corollary 5 of week 1. Now, using this limit for the norms, what we conclude is that for large enough n, the p norm of x n must be less or equal to norm of x plus 1. So, this is just by using definition of limit. Now, therefore, for large enough n, again by applying the Holder's inequality, we will end up with these nice estimates. So, our interest is to show that x n times y n converges to x times y in the L1 norm. Therefore, we are going to compute an estimate for this type of a norm. So, here we manipulate using the standard addition subtraction business, that we are first subtracting x n times y and adding the same term. So, this is not changing the original expression, but now this original expression that we are concerned with can be written in this addition structure. Now, separately using the norms of these quantities, we will first appeal to the triangle inequality. So, we will first have x n times y n minus y, the one norm of that, plus y times x n minus x, the one norm of that. So, that is the first application of the triangle inequality, but then we will appeal to the Holder's inequality and get further estimates for each of the terms on the right hand side, and therefore, what we end up with is p norm of x n multiplied by the q norm of y n minus y. So, that is dominating the first term on the right hand side, and the second term can be dominated by a term of a similar type, where we have the q norm of y multiplied by the p norm of x n minus x. So, this is where we have repeatedly applied the Holder's inequality. But now, we go back to the estimate of the p norm of x n's that we know about. for large enough n that is dominated from above by this quantity which is p norm of x plus 1. So, let us write that down and we have this upper bound estimate for the term of interest. But now, what we are given is that x n converges to x in p norm and y n converges to y in q norm. So, these are these quantities which are going to 0 and hence by this upper bound that we have obtained, since the upper bound is going to 0, we will conclude that the corresponding L 1 norm that we are interested in also goes to 0 as n goes to infinity, and hence x n times y n must converge to x times y in the L 1 norm of convergence as n goes to infinity. So, that shows that product operation can also be performed in the this LP mode of convergences with appropriate values of p. Now, we will consider the other similar condition that we have discussed in part 4. So, let us see. So, here what we are having is that the first sequence is converging in L 1 mode of convergence and the second sequence is converging in L infinity mode of convergence. So, here what we recall first is that in note 17 of week 1, we have pointed out is that if x belongs to L 1 and y belongs to L infinity, then the product is still in L 1. So, this was connected to the fact that L infinity can be identified as the dual space of L 1. So, that was discussed earlier in note 17 of week 1. But then in this case, as soon as x times y becomes in L 1, we are interested in estimating the 1 norm of x times y, and that can be dominated from above by the 1 norm of x multiplied by the infinity norm of y. So, this is the type of relation that we have also used in the previous part, the part 3 of our argument. So, there what we had used was the fact that x times y, the 1 norm of that was dominated from above by the p norm of x times the q norm of y. So, this was the Holder's inequality that we had applied to in part 3. But now, we have this new estimate involving the L 1 norms and L infinity norms, but the similar type of arguments as in part 3 will now give you the same type of convergence for the product structure, meaning if x n converges to x in L 1 and y n converges to y in L infinity, arguing similarly we will be able to show that x n times y n converges to x times y in the L 1 mode of convergence. So, this is connected with very nice algebraic properties of the L 1 mode of convergence. So, let us move on and consider the other modes of convergence. So, in this next result we are concerned with almost sure mode of convergence. Now, we will continue to assume similar assumptions. So, here what we are having is that there is a sequence of random variables x 1, x 2 and so on, and the corresponding limit random variable will be denoted by x. There is this sequence of random variables y 1, y 2 and so on. The limit random variable corresponding to that will be denoted by y, and all these random variables are defined on this probability space. Now, what we are assuming is that x n converges to x in the almost sure mode of convergence and y n converges to y in the almost sure mode of convergence, and we are going to claim that very nice algebraic operations can be done if we consider the almost sure mode of convergence. To start off with, we will consider the scalar multiplication, that if you choose any alpha from the real line, then alpha times x n also converges to alpha times x in the almost sure mode of convergence. Moreover, x n plus y n converges to x plus y in the almost sure mode of convergence, and similarly x n minus y n converges to x minus y in the almost sure mode of convergence. Moreover, the product structure still remains valid, that x n times y n converges to x times y in the almost sure mode of convergence. But further we can also consider the division operation here, but we have to be slightly careful, we have to assume slightly more conditions in order to make sense of the division. So, the first thing that we will assume here is that for all n, probability that y n takes the value 0 is 0, and similarly we will assume that the probability that y takes the value 0 is 0. And here the implication of these new assumptions will give us that we can define the division x by y, and these random variables will therefore be defined. Now, under these assumptions we can talk about the new sequence which is x n over y n using the division operation, and what we claim is that in the almost sure mode of convergence these converges to x divided by y. So, this theorem therefore lists these nice algebraic operations involving almost sure mode of convergence. Let us see the proofs of this one by one. So, the first one is concerned with the scalar multiplication. So, here the definition says that there exists a set in the domain side such that the probability of that is 0, and on the complement of that measure 0 set we will have the pointwise convergence of x n omega to the limit value x of omega. But then whenever you are choosing any number alpha, we will immediately conclude that for all such sample points small omega coming from the complement of the measure 0 set, alpha times x n of omega converges to alpha times x of omega as n goes to infinity. And therefore, on this complement of the null set we have the required pointwise convergence, and hence we claim that alpha times x n converges to alpha times x in the almost sure mode of convergence. As we shall see, these proofs are simple and just follows from the definition as long as you write out the correct steps. Similarly, let us now consider the addition and subtraction structures. First, we are given that x n converges to x in the almost sure mode of convergence and y n converges to y in the almost sure mode of convergence, and therefore, by definition there exist sets which we denote by A and B with probabilities 0, such that on the complement of the first set I have the pointwise convergence of the first sequence, and for the complement of the second set I have the pointwise convergence of the second sequence. But now what we can do is that we can look at the union of these two measure 0 sets, and then the new set which is n also has probability 0. We have discussed these type of properties earlier also. But then on the complement of this new null set, what is happening is that n complement is contained in A complement and n complement is also contained in B complement, and therefore, on the sample points coming from n complement, what we are having is that the pointwise convergence holds for x n plus y n and x n minus y n. So, the x n plus y n pointwise converges to x plus y on the complement of this new null set n, as well as x n minus y n converges to x minus y on the complement of this new null set. And hence, what we conclude is that addition and subtraction operations essentially are preserving the almost sure mode of convergence. So, therefore, original sequences as long as they converge in the almost sure mode of convergence, then corresponding additions and subtractions will also give you almost sure mode of convergence through the limit. So, let us now consider the product structures. In the product structure, we can appeal to the similar kind of a proof that we will first consider these two sets A and B, and on the complement of A union B, we can show that the product of x n and y n converges to x times y, and therefore, we will have the convergence of the product sequence through almost sure convergence. Let us clarify the case for division separately, because it requires these additional assumptions. So, what we are considering is that for all natural numbers n, probability that y n takes the value 0 is 0, and hence what is happening is that on the complement of this null set we can define this random variable x n over y n. So, for our purpose of the analysis, it is good enough that we are able to define the division x n over y n on the complement of the null set. Now, this random variable is well defined as well as x over y, and our claim is x n over y n converges to x over y pointwise on the complement of an appropriate null set. So, if you continue with the previous sets A and B as considered earlier in part 2, we will again essentially end up with the relevant mode of convergence. So, to be clear, let us write out the argument. Consider the events B n as the events where y n takes the value 0. Now, as per our definition, B n's are all measure 0 sets. Now, if you consider this new null set which is A union B, but together with union of all these new sets B n, all of this has measure 0, and therefore, the set n also has measure 0. Now, on the complement of this null set n, what is happening is that x n over y n pointwise converges to x over y, and hence we end up with the required convergence in the almost sure mode of convergence. So, therefore, what we have managed to show is that almost sure convergence supports scalar multiplication, addition, subtraction, multiplication as well as division. For the division operation, we require slightly more assumptions to ensure that the division gives you new random variables. And finally, as a consequence of this result for almost sure convergence, we are going to see similar type of algebraic structures for convergence in probability. However, recall from note 2 that we have shown that convergence in probability holds if and only if all subsequences has a further subsequence converging in the almost sure mode of convergence. And we had applied this in order to prove the continuous mapping theorem for convergence in probability that was discussed in theorem 1 part 2. Now, the same structure of the argument will give you the fact that as long as you start with sequences which converge in probability. So, x n converges to x in probability, y n converges to y in probability, then we can extract subsequences which will have further subsequences which will converge in the almost sure mode of convergence, and then we can appeal to all these new algebraic operations that we have proved for almost sure mode of convergence. And then for the almost sure mode of convergence, since these results are true, we can appeal to the characterization of convergence in probability through this convergence of further subsequence, and hence what we will conclude is that all these operations that was true for almost sure convergences will continue to hold true for convergence in probability. Meaning, if you consider scalar multiplication, then the scalar multiplication of these sequences will now converge to the limit random variable in probability. Similarly, x n plus y n will converge to x plus y, x n minus y n will converge to x minus y in convergence in probability. Again, product structures will remain valid in probability as well as the division operation, and as long as we continue to assume these conditions, we can show that the random variables exist and the corresponding mode of convergence is valid, meaning the division operation is also preserving the convergence in probability. So, in this lecture we have seen many nice algebraic operation. To start off with, we had discussed the continuous mapping theorem, and then for each of these mode of convergence, convergence in LP, almost sure mode of convergence and convergence in probability, we had looked at all the standard algebraic operations involving scalar multiplication, addition, subtraction, multiplications and divisions. We are going to stop here. We are going to continue this discussion in the next lecture. We stop here.